Electrochemical impedance spectroscopy. This course will introduce the electrochemical impedance spectroscopy technique and illustrate its use to characterize electrochemical processes. Details regarding the correct method of data acquisition and analysis, along with pitfalls to watch out for, will be discussed. Week 1. Introduction to Electrochemistry, Electrode-Electrolyte Interface, Reference Electrode, 3-electrode cell, Supporting Electrolyte, the Rate Constant, ICE Basics, Electrical Elements, Differential Impedance, Time Domain Results, Graphical Representation of Impedance Data in Bode and Complex Plane Plots, Other Techniques. Week 2. Experimental Details, Instrumentation, Single and Multi-Sign Inputs, FFT Details, Frequency Range and Resolution, Cross-Correlation, Multi-Sign, Odd Harmonics and Non-Harmonic Choices, Crest Factor, Spectral Leakage, Windowing. Week 3. Data Validation, Kramers-Kronig Transforms, KKT, Linearity, Causality, Stability, Impedance versus Admittance, Applications, and Limitations, Alternatives, Measurement Model Analysis and Linear KKT. Week 4. Data Analysis, Electrical Equivalent Circuits, Choice of Circuits, Confidence Intervals, AIC, Initial Values, Distinguishability, Zeros and Poles Representation, Charge Transfer Resistance and Polarization Resistance, Maxwell, Ladder, and Voigt Circuits. Week 5. Reaction Mechanism Analysis, Linearization of Governing Equations, Derivation of Impedance Expression for a Simple Electron Transfer Reaction, 2-step reactions with one adsorbed intermediate. Week 6. Reaction Mechanism Analysis, Continued Development of Impedance Expression for Multiple Reactions, an example reaction exhibiting negative resistance, an example 3-step reaction with 2 adsorbed intermediates. Week 7. Reaction Mechanism Analysis, Continued Development of Impedance Expression for a catalytic reaction exhibiting negative resistance, reactions with Fromkin isotherm. Practical challenges in the extraction of kinetic information, list of various patterns of complex plane plots reported in the literature. Week 8. Diffusion Effects, Warburg Impedance, Finite and Semi-Infinite Cases, Effective Change in DC Potential, and Boundary Layer Thickness. Week 9. Constant Phase Elements, CPE, Porous Electrodes. Week 10. Passivation and Film Formation, Point Defect Model, PDM, and Extensions. Description of a few selected applications of ICE, corrosion, biosensors, fuel cells, mechanistic analysis. Week 11. Nonlinear ICE, NLEIS, Introduction, Mathematical Background, Taylor Series, Fourier Series, Modified Bessel Functions, NLEIS for a Simple Electron Transfer Reaction, Reaction with Adsorbed Intermediates, Nonlinear Charge Transfer, and Polarization Resistances. Week 12. Effective instabilities in traditional ICE calculation using NLEIS methodology, solution resistance effects, detection of nonlinearities using KKT, NLEIS with Fromkin and Temkin isotherm, evaluation of related technique, electrochemical frequency modulation, EFM.